So let's conclude this review article. I jumped ahead again, so as I said, I'm being brief, but you definitely want to go and read the paper, which is very nice. It's readable. It's not terribly technical in that sense. It just keeps it's like a meta-analysis of what has happened, what can happen, what are the issues, gaps, and data issues, and so on, as we mentioned. One of the important things, as we saw in the table already, is the last mile issues. Even if you produce incredibly accurate predictions, early warnings, unless they reach the last mile where decisions are made to protect lives, livelihoods, and infrastructure, etc., it's not going to be very useful. So the last mile operationalization, communication, ethics, and decision making are very critical. The previous components in methods and techniques in the AI pipeline need to be operationalized, be robust, accountable, and fair, so they can ultimately serve serve the purpose of evidence-based policy making. Okay, so we'll look at we looked at figure 2 already. Operationalization, then again I'm reading brief parts of these sections. Operationalization strictly needs the previous layer in place in XAI, causality, and UQ for improved and accountable explanations of the predictions in early warning systems, and for enhanced disaster risk management. Calibration of MI models, especially when coupled with uncertainty estimation, aligns predicted probabilities to reflect the real-world likelihood of extreme outcomes, enhancing reliability and interpretability essential for informed decision-making. Poor calibration can lead to misguided decisions, such as overestimating or underestimating the likelihood of a critical event. So it's just a opening paragraph of this section. There are more discussions. There is more discussion that you can follow up with. Jumping ahead, communication of risk and ethical aspects are very important as well, because as I said, in the same city, for example, any area, a heat wave or a flood or a drought may not affect everybody the same way, because it depends on your socioeconomic class, sometimes on your religion, language, ethnicity, and so on. So global initiatives like the Common Alerting Protocol have standardized warning data, enabling timely alerts. There is also the UN's early warnings for all initiative. However, these systems effectiveness depends on inclusivity and adaptability to diverse community needs. Achieving this globally remains challenging, as centralized models are easier and cheaper but lack local sensitivity. AI can address this by identifying at-risk populations, optimizing message clarity, selecting effective communication channels, and overcoming the limitations of traditional one-size-fits-all methods at scale. So typically standard methods are that you have a global model which may be downscaled to a regional model for higher resolution or better resolving topography, urban canopies, etc., to produce as local as possible early warnings. But AI is now used to further downscale. Even if you have a kilometer scale model that is giving you dynamically information, integrating this for 15-minute early warnings is nearly impossible, as I said, even at a local scale. But AI can help there. So AI can downscale to street levels, in some cases farm levels, and so on. But again, there you have to be clear that you have identified at-risk populations, and message is clear, effective communication channels are established, and limitations of these traditional methods are really overcome to improve the whole system of decision making, predictions to decision making, last mile issues. Yet history shows that even actionable forecasts can fail if not communicated properly, as we said. So for this, these are issues even for dynamic forecasts. Okay, for instance, despite predictions of the Mediterranean storm Danielle's landfall 4 days in advance, the lack of effective communication contributed to the tragic outcome in Libya, where a dam broke and casualties very severe and displacement was great. Even in the more developed countries of Germany and Spain, the devastating effects of floods with more than 200 fatalities each were related to ineffective warnings. This highlights the critical need for robust early warning systems that predict events and effectively communicate risks to ensure community preparedness and response. We looked at that a little bit in table 1. The challenge of false alarms in the context of early warning systems is a significant challenge, as they can lead to warning fatigue, where public becomes desensitized to alerts and may ignore crucial warnings during actual emergencies. So it's, boy cried wolf kind of thing. If you're issuing too many warnings, people may just think there is always a warning, nothing happens. But you have to improve accuracy and location specificity and reliability of your early warnings to make sure that people take action, whether it's very severe action like moving away or evacuating during a cyclone, or just tying down things for strong winds, or saving water, or going to higher ground for floods, and so on and so forth. Model challenges then: the lack of a clear statistical definition of extreme events and the mechanisms responsible for their occurrences hamper model development and adoption. For detection, extremes usually constitute not point-wise but complex contextual group or conditional anomalies whose source, such as changing process, parents, distribution, is often unknown. This results in challenges such as capturing subtle or new patterns, setting adaptive thresholds, or integrating data across distant points in space and time, and so on. For prediction and impact assessment, AI models are sensitive to initial conditions and may not capture long-term dependencies. Training data really decides almost everything about AI models. Moreover, data might not reveal the dynamics of extremes, as there might be changes to unseen dynamics, and stationarity may not hold in general. So if you have limited data, you may not have seen all the possibilities in a changing climate, which is all too common now. Non-stationarity and distribution changes make prediction Non-stationarity and distribution changes make prediction challenging, because shifting baselines and evolving data distributions hinder models from generalizing beyond historical data. Also, relationships between variables may change over time, so even if you have trained for one period, that relation may not hold for the next period, meaning predictions often lack robustness under unseen conditions. Using hybrid models that combine data, domain knowledge, and ML could allow insights into the mechanisms that trigger extreme events. So the advantage of a dynamic model is that it can track evolving relations, non-stationarities, etc., and maybe provide training ground for AIs to constantly improve them as well, or constantly update them to the new baselines and climatologies and processes and so on. What are the and there is more details here that I have skipped. What are the integration challenges? Mixed layer models are typically and necessarily trained on high quality, well curated data sets such as Copernicus Era 5 reanalysis or cloud free satellite imagery, which often do not reflect the error prone meteorological forecasts and cloudy conditions encountered in real world situations. Era 5 is the European ECMWF reanalysis version 5. It's a blend of models and data, supposed to be one of the better ones. There are many such products. Nonetheless, you also have satellite data. They all have their limitations, but nonetheless, they are the best sources we have as of now. So recent ML approaches propose deploying domain adaptation and transfer learning techniques that find robust, physics-aware and invariant feature representations to alleviate the problem of dealing with distribution shifts. Transfer learning is basically where you learn from existing data and you transfer that knowledge into regions where data doesn't exist based on a number of rules, and it works very well with my own experience on Mumbai rainfall forecast, for example. So let's look at the second table that we mentioned: challenges, risks and needs for extreme AI needs in AI, challenges, risks, and needs in AI for extreme events. We'll look at aspects again, data, model, and integration. So extreme event modeling and understanding and trustworthiness. Now you need to transfer these to the next columns. I won't bother too much, but challenges, I won't read all of these, but we are looking at challenges, risks, and future AI. Manage inconsistencies, biases in data, handle multimodal data from diverse sources, accommodate variations in data resolutions, handle sparse occurrences of extreme events, sampling issues, adapt to evolving data sets. That's the top one under data. Risks, lack of sufficient data with expert annotations, low number of samples for the anomalous cases, difficulty in defining what constitutes an extreme event, and lose critical extreme values when pre-processing. So you don't give raw data to AI models, you always do some pre-processing, but you have to be careful there to make sure that extreme events are spikes. So when you're dealing with data with spikes, our normal standard techniques may begin to wipe out certain important information. What is the future of AI in this case? Transfer learning, which we mentioned, class imbalanced and low shot learning. These are typical technical terms that I'm not going to get into. Long tail learning, so the distribution, have long tails, which means extremes are possible at very anomalous, extremes of extreme anomalies are possible, 99th percentile or even higher percentile. Online and continual machine learning is the future AI. Let's jump ahead to integration, scale to large data sets and real scenarios, generalization and transferability, bias, transparency and fairness, which you have mentioned, human AI interaction and decision support. So how interactive is the tool, AI tool, for decision makers, because they don't always have a deterministic one-shot decision. They have to consider many options and then consider what happens if we make this decision versus that decision, opportunity costs and risks and so on. So you need the human AI interactions. Communicate and manage uncertainties, of course. In terms of risks, data quality, availability, complexity and interpretability are issues. Lack of domain expertise and collaboration in going from AI outputs to decision makers. Lack of domain experts, as we said, outputs difficult for non-experts to interpret or trust. Missing uncertainty quantification for models and graphs, so you shouldn't let people think that you are giving a very precise answer. If there are probabilities around them, they need to know that. Unintentionally perpetuate biases in decision making, so certain regions, groups, neighborhoods may get neglected if the data is trained that way, or AI is trained that way. Resistance to use AI-driven decision support systems is still a big problem. But the future is that you have domain adaptation, replicability and validity, and humans are in the loop, libraries and improved implementations. So you have lots of simulations done and analog decisions can be made to say where we are going now and what happened in a similar situation before. It's called analog. Distributed solutions and federated learning. Distributed solutions means it's not one size doesn't fit all, and federated learning, so model calibration and uncertainty quantification, large language models, which we mentioned, AI for perception and reasoning. Okay, this is a long caption for a figure we are going to look at, but I will try to explain without putting you through the whole caption. Summary of case studies using AI intelligence to manage extreme events. There are also case studies at the end of the paper that I'm not going to go into, but basically here are 4 case studies looking at drought, heat waves, wildfires and floods, and they are showcased here where AI enables detection, forecasting, impact assessment, explanation, understanding and communication of risk, providing a comprehensive solution for disaster management. So droughts, multimodal data, satellite imagery, climate variables, static features like land use, are combined, and you go through precipitation, sea level rise, main I made it too small, so even I can't read it now, but detection and explainable AI using neuron integrated gradients. So you have air temperature, soil moisture, vegetation coming into the ML model. You are doing drought modeling and integrating forward in time, and you are tracking now features in time. Here are the real times given in, this is 2010, 0105. So let's see, 05 is changing, so 01 is no, they are at different time steps. So 01, 05, 06, these are same year, but 01, 06, 14, 11, 21, and so on and so forth. But just look at air temperatures, soil moisture, and vegetation health. These are the indices used in the model to from the data to predict drought, and the outputs also include air temperature, soil moisture, and vegetation health. You may be trying to manage a piece of forest, cropland, and so on and so forth. Okay, example of heat waves. Feature extraction, so you can see the differences in the models for drought versus heat waves versus wildfires and floods. So here you have time series, data cubes, and text fed into feature extraction. Features are tabulated, then prediction with dimensionality reduction, which is an approach to make things simpler. So data cubes, encoder, ML model, predictions, and a decoder. So there are data cubes again. These are technical details. Even though I said there aren't many, there are some, so I'm not going to go into these. But feature analysis and selection happens as well. You can see there are time lags, duster. So what are these things? Basically just focus on predictions from selected features. These are ways in which features are analyzed and selected for feeding into the ML model for making predictions. So just get an approximate sense. If you are a technical expert, obviously you want to go and read, because these details are not even in the paper. They are referenced, and these are schematics of those references. Wildfires and pyro CBS. Wildfire prediction and explainable AI, climate, anthropogenic and other topographic information, weather and vegetation model of vegetation data going into mixed layer model. Wildfire model then looks at fire danger map, burned area, area affected, intensity, and so on, to give you output on saliency map, feature ranking, uncertainty map, and so on, and other details here. Floods, ML generated model. You can see AI and risk communication here. Pre-flood satellite image, flood map. With ML, you are going to give post-flood satellite image. So AI generation of reports for preparedness and mitigation with time series, data cubes, and text used to train. It's like a navigable tool, so a mayor can sit in his office with his team and try to see where flooding is going, whether a school is getting inundated, whether a hospital needs to be evacuated, roads are going to be closed, trains are going to be shut down, and so on and so forth. So jumping ahead to conclusion and outlook, we will look at a little bit more text, but I'm being very brief, as I said, so try to get a good sense or read the whole paper if you are interested. This review highlights the significant potential of AI for analyzing and modeling extreme events, while also detailing the main difficulties and prospects associated with this emerging field. Integrating AI into extreme event analysis faces several challenges, including data management issues like handling dynamic datasets, biases, and high dimensionality that complicate feature extraction. Remembering that data itself is never sufficient, especially for local scales. AI models also struggle with the unclear statistical definitions of what is extreme. Furthermore, integrating AI with physical models poses substantial challenges, yet offers promising opportunities for enhancing model accuracy and reliability. Trustworthiness concerns arise from complexity and interpretability of ML models, the difficulty of generalizing across different contexts, and the quantification of uncertainty. Operational challenges include the complexity of AI outputs, which hinder interpretation by non-experts who often make decisions, resistance to AI adoption due to concerns over reliability and fairness, and just inertia in the system, and of course the need for frameworks that facilitate transparent and ethical integration of AI insights into decision making processes. This will happen over time, but things are moving fast in terms of climate change and what AI spits out, so we have to keep moving fast as well in terms of using them for decision making. The previous challenges compromise the reproducibility and compatibility of ML models in analyzing extreme events. I jumped ahead. These challenges are exacerbated by data scarcity that we mentioned, lack of transparency in model configurations, and the use of proprietary tools which are black boxes which you cannot interpret. Additionally, interdisciplinary differences hinder consistency and compatibility. So even here you can see models are different for droughts, heat waves, wildfires and floods, and yet droughts, heat waves and wildfires can be intimately related to each other and co-occur. So we have things like compound events which are even more difficult to manage. Okay. Effective solutions demand robust, transparent methodologies, inclusive data sharing practices, and frameworks that support cross-disciplinary collaboration. In this view, we overviewed and emphasized the importance of developing operational, explainable, and trustworthy AI systems. Addressing these challenges requires a coordinated effort across disciplines involving AI researchers, environmental and climate scientists, field experts, and policymakers. This collaborative approach is crucial for advancing AI applications in extreme event analysis and ensuring that these technologies are adapted to real-world needs and constraints. From an operational perspective, adapting AI solutions to real-time data integration, model deployment, and resource allocation highlights the need for systems that can function within the operational frameworks of disaster management and risk mitigation. Besides, methodological improvements are still needed in model evaluation and benchmarking to alleviate issues like overfitting and enhance AI systems' generalization capabilities. Looking forward, there are significant areas for further exploration and improvement. These include the development of benchmarks specific to extreme events, enhanced integration of domain knowledge to improve data fusion and model training, and the creation of robust, scalable AI systems capable of adapting to the dynamic nature of extreme events. So there are AI experts who develop AI tools, and then people who apply AI tools, then people who use the output. So there has to be a feedback so that domain experts don't work in silos. So there is continuous improvement of the end-to-end system to the last mile. Recent LLMs harvest vast amounts of did I jump anything? No. Vast amounts of domain knowledge embedded in the literature, promising significant advances in communicating risk. As we advance, the ultimate goal is to harness AI's potential to substantially benefit society, particularly by enhancing our capacity to manage and respond to extreme events. Through dedicated research and collaborative innovation, AI can become a cornerstone in our strategy to understand and mitigate the impacts of these challenging and elusive phenomena. Obviously, AI is now here, and it's here to stay, and it's an integral part of everything we do already, including observation systems, IoT, etc. But we have to exploit the best of AI, make sure we minimize any potential negative outcomes or unintended consequences, biases, and deal with uncertainties, because there is really no risk-free option. Risks are here and they are dynamic. System is complex and ambiguous, so we need to use all the tools that are available and constantly keep monitoring them, evaluating them, and improving them, and so on, right? So let's conclude this paper with that sermon.